Chapter 3 on Agda and intuitionistic type theory. The first thing I want to tell you is that during the weekend I did a little bit of replanning. I am afraid I have gone a little bit more slowly than I planned. It was a little bit difficult to know how quickly you go through, especially showing this Agda code and demonstrating Agda. So I decided to, make all the files public that I was intending to show you. I realize that I won't be able to show you everything, but since everything is super important, in order to get a kind of comprehensive grounding in the type theory behind Agda and in fact Koch. There will be things that I won't be able to show you, but you can at least look at them yourself. So these are all the things, and as requested, there is also a tarball with all of it. Some of it, I must admit, is a little bit preliminary, and I think in the tarball there are even some incomplete files which you can complete as an exercise. I should also say, that I had this basic reading by Martin Löw and in our Stanford Encyclopedia article. I'm especially interested in feedback on the Stanford Encyclopedia article because it has not yet been published, and any feedback on how readable it is, or what if you think that something should be presented differently would be very valuable for us. But I would also recommend, a little bit self-centeredly, my own papers on the syntax and semantics of induction recursion. I had maybe hoped, optimistically, to show you some details of that at the end of the course, but I will unfortunately not be able to do that. I especially actually recommend the talks. The talks are easier to read than the papers. So for example, if you're interested in induction recursion, I think the paper where we first presented it, the finite axiomatization of inductive recursive definitions, is fairly readable. Of course, it's not so long, so in order to get more details, you have to look at the paper. But as an introduction to the paper, I think it's actually quite readable. And there are also some papers on one paper on generic programming, because I, together with Anton Zetzer, we showed how you could internalize the whole theory of inductive and inductive recursive definitions in a completely finite form. We have a universe of codes for inductive and inductive recursive definitions. So the first aim with this was just to show that you can act completely precisely in a finite way encode this very, very powerful theory. But it had a kind of side benefit, and it is that since you have now a type of codes for inductive and inductive recursive definitions, you can actually do induction over that type of codes. And this becomes a kind of very disciplined approach to so-called data type generic programming. And in this paper, together with Marcin Benk and Patrik Jansson is a specialist in generic programming, more sort of Haskell-style generic programming. We show how you can do that for various universes, classifying, small classes of inductive definitions, like just, for example, what is traditionally called homogeneous term algebras, where you just have constructors with an arity and natural numbers. It's a sort of very easy special case of inductive definition. And then we show how you can sort of make more and more general universes, including parameters, inductive families with indices, and generalized inductive definitions and so on. So also this paper, I think, is quite readable: generic programs, generic proofs, and dependent types. And in this paper, we prove a very important theorem. It takes the whole the whole talk, you know, and it's very, very complicated at the end, you know. So we knew equality wasn't easy in type theory. So this is, but it's the introductory slides there are, I think, quite good to read. Okay, so let me show you. Yeah, so, okay, back to where we were. Okay, which perspective was it that I was going to show you? Was it the Swiss perspective? It was a Swedish perspective. The Swedish perspective is kind of back to basics. So I can't really show you the Swedish perspective without actually showing you exactly the canonical form of Martin-Löw type theory. I type checked, wow. With a canonical choice of names of the data types, and with a canonical choice of letters for the meta variables, you know. This is how you tell a real type theorist from a modern type theorist, that real type theorist says little a colon big A and not little t colon sigma. Anyway, sorry for silly joke. Yeah, so I have done a module here with exactly, I mean, this is as close as I can get to what Martin-Löw decided that Martin-Löw, what intuitionistic type theory should be, a day in March in 1986 when he shocked everyone. He became intentional again, you know, and this is the way it was a mistake, extensional type theory, forget about it, never mention it again. It's supposed to be intentional, it's supposed to be formulated in this logical framework style. So this is how it was. I mean, so last time I presented to you, well, in the first lecture I presented the logical framework. I told you a little bit about how you program in this, and I also told you that you can actually use it as a logical framework in the sense that you can conveniently encode a lot of standard logics like you know, you could encode, for example, piano arithmetic. It's completely unbiased to whether it's classical or intuitionistic logic. You can encode ZF set theory. You can encode Church simple type theory or higher order logic as, you know, the foundation for systems like Isabelle and the different versions of the HOL system. I also showed you, you know, the types, natural numbers and Booleans, and I told you that in this way we get a system for proving theorems or constructing functions in Gödel system T, you know, the system of primitive recursion of higher types, where including the Ackermann function. I then showed you how to do predicate logic with equality. So what we get here, if we put all this together, is that we get a very, you know, famous standard logic, or at least embedded in this way, Heiting arithmetic, yeah, PA, piano arithmetic. So Heiting arithmetic is, you know, intuitionistic predicate logic plus the piano axioms. And actually we get a little bit more because, you know, Heiting arithmetic has only, it's a, you know, unityped system with only natural numbers as a type. But of course we get immediately here higher order functions over natural numbers, and we get a system called HA omega. But it's all very, you know, traditional logic, sort of pre-Curry-Howard type of thing, which is of course encoded in a Curry-Howard style, so we get predicate logic with proof objects. But we don't really mix. We don't really mix the propositions and types in this. So this was really sort of things which existed, of course, and which were already, here you have some of the most famous systems of all of mathematical logic. So this already existed before the late 1960s. They are all sort of pretty old, sort of turn of the century, 40s type of things. So what of course happens when you equate propositions and types, or in Agda parlance, propositions and sets, is that whatever construction you have on propositions, you can use on types, and vice versa. So last time I showed you an implementation of predicate logic with sort of syntax following the standard of predicate logic syntax. When type theory is designed, you choose notation more on the type side, on the set side. So for example, Martin Löw chose to call the empty type N0 and the one element type N1. Then of course he has N2, N3, N4 and so on. But in Agda we have not got room for infinitely many things that he had on his paper with ... dots. So instead, as we shall see, we can have a family of type of finite types. Which we usually call fin M in modern type theory. What you also do is that you take the rules of predicate logic and you generalize them to the appropriate dependently typed version. So for example, when we had the rule of absurdity elimination in predicate logic, we just had a constant proposition C, which was called phi, I think, but now it's a predicate. And you do this uniformly for all type formers. I won't go through this in detail because I'm sure you can, if you don't know them already, that you can imagine or you can study them. I'm choosing exactly the syntax used by Martin Löw, to I and J for the constructors of a disjoint union, D for the case analysis. Sigma type had an eliminator that he called E, which is pattern matching on a pair, which he considered more primitive than the projections. So Martin Löw tried to somehow make all the constructs being looked at as inductive, so all defined by their constructors, and then the elimination rules were all designed to somehow analyze the constructors. The other view of the sort of co-inductive, or the view of sigma, or the right adjoint, if you want to talk in categorical terms, is to see the sigma type as being defined by its eliminators, the first and second projection. But actually, so which you can define in terms of the E. It's sometimes called split, which is actually not derivable from the projection, and so that's instead taken as a primitive. And even in the most extreme form, even the dependent function space is now looked at as being inductively defined, and lambda is the constructor. And then you get this somewhat strange but powerful eliminator, which pattern matching on the lambda constructor. In some sense, this is only of historical interest, because this there was a lot of excitement of this when in the 1980s when this was invented, but in practice this is not really used. Yeah, and then of course the identity type. I know that Bob already talked quite a lot on the identity type. And of course, if you want to follow the developments in homotopy type theory, it's very important to that wasn't good. That's bad at typing. It's important to know about the rules for identity types. So as I said last time, the identity type was actually not there in the original version of type theory. It came in the second consistent version. And it's actually not as innocent as one might think. It's actually quite a quite a controversial step, as history has shown. You say that you define identity on any type just as inductively as with one constructor for saying, just that it's true that little a is equal to little a. And of course, one might somehow question, does this really make sense if big A is a function, or some W type, or a universe, or something like that? It's very brave to do this. Yet, this is what we consider the standard version of the identity type. And then you get this kind of rather complex operator, which I call J. So I decided, So Martin Löw, he defined the identity type from the perspective that it's the least reflexive relation. If you define it as the least reflexive relation, you actually don't get this as the natural elimination constant. So instead I shall show you. I have a file here with identity elimination variations. So actually this is what he defined in his original papers. It's somehow, you think of this as proving something about an identity, a property of an identity. You prove it for x's that property C holds for for the diagonal for when the two arguments are equal. And then in order to make it suitably general, we have to have a third proof object. It has a proof object, that one. And in this case, the proof object should be the reflexivity constructor. And here actually, here I get occasion to illustrate another of Agda's features, which someone asked about last time, about Agda's dot notation. So in the equation for the what Martin Löw called the J operator, J Martin Löw. When you pattern match on the recursor, you know that the two indices, the two x and y's here that you try to compare for equality, they will be forced to be equal. And Agda denotes that by putting a dot on one of them, the one that is somehow forced by pattern matching to be equal to the other one. So it doesn't, it sort of signifies that there is no choice. There is no choice. It's uniquely determined. Right. So this is how he had it, and I think it's also very important to try to put yourself a little bit in Martin Löw's shoes. That the theory is very much designed to be some kind of very beautiful systematic theory where there is a very clear idea about what is a formation rule, what is an introduction rule, what is an elimination rule, what is an equality rule, and that this should all be schematic. So in fact, just before Martin Löw had his first version in 1971 of type theory, the one which was inconsistent with a type of all types, he had written about inductive definitions in predicate logic in natural deduction. And he had showed how you could have a schema for inductive definitions, which somehow corresponds very much to what you can do in type theory. You have inductive predicates, and he had the notion of what you call generalized inductive definitions, where hypotheses can themselves be hypothetical, like what I will show you later. So he knew that for predicate logic, you can formulate such a general theory, and he also showed a normalization theorem for that version of predicate logic. He called it a Hauptsatz. The paper is called Hauptsatz for an iterated theory of for an intuitionistic theory of iterated inductive definitions. But then when he wrote his papers, although he was very much motivated by these patterns that he had discovered for predicate logic, he did not spell them out. Yes?
Is this J derivable from the previous J? And
yes. Yes, this J is easily derivable from the other J. The other J is derivable from this J in a complicated way. So it's better to work with the other one. So although I'm a little bit ahistorical in putting the other one on the main page, I think everyone should get the message that the other one is the best one. It's good to know this for historical reasons, but the other one is clearly the best one. So if I go back to this one. So this one was invented by Christine Paulin, who is one of the main people behind the Koch system, who realized, when they were working on the design of the calculus of inductive constructions, that there was an alternative definition of equality. When you fix one of the arguments, do you think I can jump so high? It's track and fields, yes. Ooh. Yeah. High jump. Anyway, you see the little a there in the about 8 feet above the ground. It's now a parameter, and then the elimination rule changes, because now you are just somehow you are looking at it as the least unary predicate of things equal to little a. So then you just need to prove, to prove a property for an arbitrary b, you prove it for a. And this is, of course, exactly the rule that you inherit from predicate logic, the rule of substitution of equal for equals, enriched with a proof object that you, of course, usually don't use, but in advanced situations you can use it. And of course the miracle is that, well, this kind of thing, it goes quite far, and the miracle is that it turned out that this J operator, or actually the other one I think people were working with, was able to derive all these complex structure that people work with in homotopy type theory, the weak omega groupoid structure of the iterated identity types. Yeah, so that's another point to be made, that I don't think that Martin Löw, when he designed the identity type, particularly cared about the fact that the type A here can itself be an identity type. I think for years and years nobody talked about this. This was just some kind of anomaly. You just wanted to have something uniform identity for an arbitrary type, and it just so happens that you can iterate it. But of course it's sort of, completely analogous to what people already had done with higher category theory. You don't only have objects and arrows, but you have arrows between arrows and arrows between arrows between arrows. And in homotopy theory, where you have path and you have homotopies and you have homotopies between homotopies, etc. So that was how that connection somehow came in, perhaps a little bit by chance. Yeah?
That A in the argument is, that's just suggestive, right? It's saying little a.
Yes, let's see. So you mean This one, yeah.
Implementation subject.
Yeah, here.
That A.
Yes.
Is a suggested name for the key parameter.
Oh, you see, okay, so that's, yes, exactly. So this is, yes, it should really be B.
Okay.
It's, you know, actually it should be an underscore. Yeah, exactly. So that's, thanks, that's misleading. Yes, it should be a B. Yeah. Anyway, you know, so this is what we should think of as the canonical identity eliminator. But of course, you know, Thomas Streicher realized that it's somehow not complete if you think that it should be, you know, if identity is defined as the least reflexive relation with one constructor R, it sounds as though it has one element. But you know, Streicher and Hoffman, they realized that, you know, I think they probably tried to prove it, but they realized that it cannot be proved with a J. And they constructed this groupoid model, which showed that it's actually not derivable. You know, there is a model where there is more than one element in more than one identity proof. And then he discovered that, you know, you could complete this by introducing the so-called Streicher K. The missing case is that you want to somehow to have a special case for proving things about the diagonal when x is equal to x. This is apparently not derivable, but otherwise the rule is just like a simplification of the other one. And yeah, so I think Streicher has had it, you know, as more like Martin Löw, and then you could do it more like Christine Paulin, and then it becomes simpler. And what is interesting about it is that it entails uniqueness of identity proofs. So yeah, here's just a little Agda program which more or less shows that you can define, you can prove that, yeah, so maybe a little smaller here. What it says on the top line there, the bottom line we should use, is that any proof C, any two proofs P and C of an identity are equal or identical. And you know, I won't go through this in detail, but if you're interested, you can study this, or even better, do it as an Agda exercise. Yes, of course, as usual when you study mathematics, the best exercises is to cover the proofs and do them yourself. So, yeah, and same thing with learning Agda. Okay, so let's go back to Martin Löw type theory. Natural numbers I won't sort of bother you about. He called it big R instead of rec or natrec, the eliminator. But more interesting and very important is the W type. Did Bob talk about W type? Bob, did you talk about W type? No, he did? No, okay. So this is something important that also belongs to the, you know, somehow part that you should know if you want to have a comprehensive knowledge of type theory. Although, you know, of course, these so-called generalized inductive definitions, W type. So Martin Löw called it a type of well-orderings, which is perhaps not the best name for it, because usually of a well-ordering one thinks of a total ordering. So better to call it a type of well-founded trees. And it's the first time type theory, it was introduced in 1979. It was not there in 1972 or 1973. It came as an afterthought. There was a special case of the W type actually introduced already by Dana Scott in 1970. But it came into Martin Löw's version of type theory in 1979. And we call it a generalized inductive definition. So what is generalized about it? Well, yeah, so let's see, so now it's all a little bit unreadable here. Sorry. Yeah. I hope this is a little bit more readable. Yeah. Anyway, so first of all, you know, it takes two arguments as parameters, and it has one constructor. And you know, so the first we think of as a side condition, little a in big A. The other, you know, is somehow where the induction happens, or the, you know, the reference, it's the circularity, the reference to previously built W types. And what is generalized about it is that it's a function type. It's, you know, it's got an arity. This constructor has got an arity which is indexed by a type big B of little a in the little a in the big A. And what this gives you is somehow almost the most general possible type of well-founded trees that you can imagine. And there is a precise sense in which this is the most general thing you can have. So it is the type of varying, well, type of trees with arbitrarily varying branching. So the big A you think of as an index type. How many different ways, how many different numbers of subtrees can you have? So for example, if you say 2, 3 trees, you know, there are 3 cases: leaf, 0 kids, 2 kids, and 3 kids. So, you know, then you take A is equal to a 3-element type, you know, which is n1 plus n1 plus n1. And then, you know, you say that B of, if we call the 3 elements 0, 3, 1, 3, and 2, 3, 0, 3 is n0, that's the leaf. 1, 3 is when there are 2 kids, and 2, 3s is when there are 3 kids. There is something called the Brouwer ordinals, which is in some sense the simplest version of a generalized inductive definition. It's when you add to natural numbers a third constructor which says that for any sequence of natural numbers there is such an ordinal. So I actually have it in the file, but let's just define it as a special case of the W type. So if we take instead, Brouwer ordinal, there are also three constructors. There is the 0, which is a leaf. There is the successor, which has 1 kid, and there is the limit, which has an infinite number of kids. So it's trees, it's sort of a bit like 2, 3 trees, but it's sort of 1 omega trees. You know, internal nodes have either one kid or infinitely many kids. And this is called Brouwer ordinals of the second number class, and it's something which goes back to, you know, the early part of the 20th century. Then there is the second number class, you know, where this is itself the Brouwer ordinals of the second number class, etc. So they are all captured by the W type. The only problem, you know, so we say what W type is completely general for defining inductive types. So why do we need all this business with inductive definitions and, you know, inductive data this and blah, blah, blah? Well, first of all, it's of course convenient to have them as a special syntax for them. But also, the theorem, which says that any strictly positive inductive type can be encoded as a W type, it relies on extensional equality. So it can be done in extensional type theory, but not in intensional type theory. You cannot derive the rules in intensional type theory. So this was one motivation to develop type theory as a general theory of inductive types. And of course we saw Adam making beautiful use of one aspect of the generalization, the inductive relations, generalization of inductive types. One may ask, why didn't Maslov do it himself? And I think the reason is that actually it was not so clear what would be the rules of these special cases in the first place. Well, there were all these 5 versions associated with different years. And it was only somehow when that came into its precise place that maybe it was time to design it as a general theory of inductive type. And that work really started at Cornell with the work of Bob Constable and his student Max Mendler. And then it continued, and I was involved, and it also led to the calculus of inductive constructions. But I think that's somehow the way the history went. But even if you cannot encode arbitrary inductive types as the W types, it's still good to know that essentially the general form of an inductive type is like a W type, but only with a sort of rather trite generalization. So general schema or general shape of inductive type. So now in the first instance, I will talk about inductive types. I will not consider inductive families or induction recursion or parameterized inductive type. I just take the simplest thing, inductive type. But I will, so let me write it in, I will first just take the very simplest thing where we don't have generalized inductive definitions. So you have, data called ind :set where. And then you're allowed to have arbitrarily many constructors, so C0, C1 maybe, to Cn. And what is the general shape of a constructor? Well, it should always return an element in the inductive type or in the inductive set that we are defining. It can have arbitrarily many arguments, but some of them are like the little, the big A here, what we could call the type of side conditions. If somehow terminology familiar from, logical definition of logical systems, you distinguish between the proper premises of a rule and the side conditions, which are usually written on the side of the rule. So this is what's going on here, that, this is like the little b should be above the line and the little a should be to the side of the line, if you sort of follow that kind of convention. So each constructor can have arbitrarily many arguments, but they are classified as either side conditions or as inductive premises. So let me just write one generic one here for a side condition here. And then there are the inductive premises. And in the case of an ordinary inductive definition, this is just it just refers to the type we are defining ourselves. So somehow inductive argument. So this is, shape of ordinary inductive definition. You can put the side conditions and the inductive arguments, you can essentially put in arbitrary order. Although for this particular case, there is no there is nothing gained by putting them in arbitrary order. You could actually put all the side conditions first. This is no longer the case when you generalize this to induction recursion, where the inductive arguments can depend on the side conditions. So in a generalized inductive definition, we can here have a function, which that this argument can correspond to a branching. So we now have b of x to ind here. I don't know, it got very small. Can you see what I'm writing? I will. There. So you see that it's exactly the shape of the, I don't know, with the same notation. It's exactly the shape of the W type, except that there can be several side conditions and several inductive arguments. So this is somehow the discipline that your inductive types should adhere to. And I think that it is this that Agda's positivity checker checks. I am not absolutely sure that it exactly adheres to this, but roughly speaking, at least, yes.
So the inductive argument here, I could say any number of PAs, because there's more than one.
Yeah, thank you. In general, there can be any number of those as well.
And they don't have to be the same B.
No, they don't have to be the same B. So sorry. So it's yet another of these kind of somewhat inessential, because you could actually put them all together by a sigma type, and similarly with the side condition. But of course, in practice, you would like to have this flexibility. So this is the general shape of a generalized inductive type. I think I will talk about inductive families, the general shape of inductive families, while I have this on the board. Maybe I should just, because it just so became a little bit messy. So let me just write it a bit larger. So you have C1 here. You have an argument here. You have, maybe I should write it in, what I do on the screen when the types get too big is that I do them vertically. So maybe I should do that here too. So we have an arbitrary side condition. We have an arbitrary inductive premise, which is B of A arrow ind. Arrow ind. Yeah, and of course, there should be more dots. Like that. Yeah, so actually just another little story that, I realized this thing that there is something more general called an inductive recursive definition. I did that after having refereed a paper by Max Mendler, and I was at Zurich airport, and I had a flash of insight, and I thought, oh yes, you can generalize this, and in this way you can capture a whole lot of previously unrelated definitions in type theory. And I wrote this paper called something like A General Theory of Simultaneous Inductive Recursive Definitions, where I explained the general shape of an inductive recursive definition in this style. And unfortunately, the paper made a lot of use of dot of ellipses. So it took years for people, it seemed like nobody, I had the feeling that this was something really quite important, but it took years before I met anyone who also thought it was important. But the people who thought it was important were people coming from proof theory. So like Anton Zetzer is a proof theorist, and there is another proof theorist called Mikael Rathjen, who is a very strong proof theorist working in England. And they say, yeah, this looks really interesting, but we don't like the dots. For us proof theorists, we want it absolutely precise. We want to remove all the dots. You know, proof theory, it's absolute honesty. So, and that's how I started working with Anton Zetzer on the topic of removing the dots, and this is how, you know, we came up with this idea of a universe of codes for inductive types, and this is what those papers that I pointed to earlier are about. Okay, so that was an aside. If we have an inductive family, you know, then we generalize this. So, what should I call this? I. Yeah, and again, you know, dot. C dots. Set. So in an inductive family, you define a family of types, and there is at least one index set. There can be more of them. So this is the index set. So it's something you can define before, or maybe turn into a parameter. And actually, the schema for this is really not very different. The only thing you need to do is that you need to take into account the fact that it's now an inductive family, so it needs arguments. As many as it says. And in particular, the argument of type I is, what shall we call that? Little I. Yeah. I hope you see what I mean in any case, right? Now, maybe that's not good, actually. Maybe I call it C, because it can be an arbitrary term of that type. And here can be yet another term. Yeah, like that. And of course, you know, there can be lots of these terms. So for example, you know, the things that Adam defined the last hour are special cases of this, where, you know, you put in some terms here. I will, when I show some examples of inductive families in a bit, I will point you to the point where these are. So this is, you know, the general notion of an inductive family. And then you should say that all inductive definitions and inductive recursive can have arbitrary parameters. There is in fact no restriction at all on the parameters. There are, you know, if you look at in our papers, you will see that there are various restrictions about sethood on these different constituent types that you use in the definition. That's so that we mustn't somehow break the size condition. You know, they have to be small in some sense. If we want to define a small inductive type, something which is a member of set, then there are constraints on what the index types and the, you know, the branching of the constructors here and on the side conditions, what they can be. So Agda allows, you know, inductive types not only in set, but Agda has also bigger universes that it allows to define inductive types of higher universe. This is somehow nothing which is, you know, it's nothing which has somehow been discussed in the literature in theory, but it's quite clear that you can do it. So let me say something about induction recursion as well. I will not sort of make this picture even more complicated by saying how the schema for induction recursion, what it looks like. But the great thing is that it's almost the same. The only thing that happens is that when you build these little a's and big B of a's here, then it can depend on a simultaneously defined function which goes from, ind of something into something. So, so maybe I was a bit quick there. Usually, with inductive types is that you first define a type inductively. Then, once you know how some data structure is inductively generated, you can define functions by structural recursion on the way the elements were generated. This is expressed by the elimination principle. And you can write it in AGDA by pattern matching. The thing about inductive recursive definitions, and now I think this is a good point to show an inductive recursive definition, is that contrary to somehow what one might have thought before, it's quite possible to let the function that you define by structural induction on a type participate in the typing of the constructors of the inductively generated data type. The origins of this is, the first time this was used was in type theory when one introduced the so-called universe a la, I think I will erase this now, only sort of, or maybe I shouldn't. No, okay. I was just going to write a la Tarski. I talked about a la Russell. So the universe a la Tarski can be defined as a type internally to, as a member of the type set. And the difference is that when you have universe a la Tarski, then you distinguish between a code for a type, which is an element of the universe, and its meaning as a type or as a set. So you actually have a decoding function taking a code into its meaning. So here in this AGDA code, I have used small letters for the constructors of the universe. So N0 is the code for the empty type. N1 is the code for the one element type. The circular plus is a code for types built by disjoint union, little sigma for big sigma, little pi for big pi, little n for big n, little w for big w, and little I for big I. And then you see how they are decoded here, saying exactly what I said before, that little n naught is decoded as big N naught. And the surprising thing here, which one might have thought was absolutely wrong, is that if you now look at the typing of the little sigma, pathetic jump, then, it says here little a in U, that's very normal, and then the generalized premise has the type T of little a arrow U. And of course, you should be worried about this, that, we have something, T is not defined yet, and it's to the left of an arrow. You shouldn't do this. There are computer scientists who have destroyed their careers by thinking that anything you can write with rules, even if there are implications above the line, is meaningful. If they hadn't, taken a course in monotone induction or kind of being more careful, they might have thought that anything you can write is good. Of course, in Haskell and ML you can write anything, but we know that there is a complicated reason why this has a meaning, which is so-called domain theory, where you can have these things with negative occurrences, but they don't generate sets in the normal sense of the word. So you should be very worried about this. So I think that when Martin Löw introduced this in give you another year, 1980 or something like that, then he knew that it was okay. He had actually used it earlier in his 1972 paper there is a proof of normalization for the very first consistent version of type theory. It actually uses induction recursion, but not as a formal construct, but as an informal construct. But he already at that stage had, the idea that all the meta theory of type theory should be done in a constructively valid meta language. And I think he believed that in some extension of the type theory he was working on, this notion of, this normalization proof could be formalized. But he didn't say how, and it's a little bit non-trivial how to do it. It's even a little bit non-trivial to show that it has a good set theoretic meaning. Martin Löw did not care too much about set theoretic meaning because, of course, the whole point was to provide something which was more secure than set theory. So there is nothing in Martin Löw's paper about why this is a good monotone inductive definition in the sense of set theory. But certainly he had some good intuition why it's a good constructive definition. So the people who actually proved that it had good set theoretic semantics was Peter Axel and a guy from Cornell, Stuart Allen, with two different constructions. You can actually show, that you can give it set theoretic meaning. Yeah, so this is another aside that I came to think of that is important, I think, for you to know, and that is that type theory, Martin Löw intuitionistic type theory, has straightforward set theoretic semantics. If you interpret all the constructs of Martin Löw type theory in the most possible straightforward way, like type theoretic natural numbers are set theoretic natural numbers, usually called omega, that, for example, the type of functions between A and B is interpreted as, let me just finish the sentence, as the set of all functions in the set theoretic sense. That is relations with the unique existence property. Then it's okay, yeah.
Is T allowed to be an arbitrary function then?
T is allowed to be, T here is the function which is defined simultaneously by recursion on the type. So it has to be such a function. It has to be somehow, it has to be defined by some notion of properly generalized primitive recursion.
So could I have T as just a constant function as a certain U?
No.
Okay.
No. It should be something which was a good type before U was born.
Okay.
Yeah. That's yeah. If you want to sort of do this completely formally correct, you have to say such things, right? And that's the kind of details which are in those papers that I was pointing to at the beginning of the lecture. Yeah?
Is this definition of syntax complete for being able to implement all of the usual operations like substitution?
Let's see, so substitution in what sense do you mean?
We have an element of U that we think of as having a free variable, and we'd like to substitute a concrete term for it.
So let's see if I understand. So you have, yeah, I think I'll kill this now. So you want to define an operation of substitution. What type does it have?
I think in this encoding you would have some type like T of A arrow U. And we also happen to have another argument, a U, so parentheses around that type is also U.
Mm-hmm.
Get a U back, something like that.
Yeah. So okay, so I see what you mean. Yes, and A would be in U, of course, like that. Yes, and now you would want Yes, so you would want subst A, should we call it here? I don't know.
But the function
B.
U, not really a U with a U pre-variable. It's just a U with a pre-variable of a value, not a function.
Yes.
It doesn't really make sense.
Part of my question is how you recognize this operation, which is a normal and important one you want to use on syntax or terms in any language.
Well, it could be U to U, the U with a pre-variable, with a pre-type variable. So in that sense, substitution is just the case.
So, what I should say is that, of course, you can think of the codes as a kind of generalized syntax for types, but it's not syntax in the ordinary first-order sense, because it's a syntax where, you know, things like sigma and pi have infinitely many arguments, possibly, right? They have sort of generalized inductive definitions. Let's discuss this a little bit more in the break, and maybe we can. Maybe Andrea has already given the complete answer, but I'm not as quick, so we can see if there is more to say about this. So the definition is certainly supposed to be complete for the definition of what the universe is, and this is the definition of the decoding. Then you can also have a general operation of universe elimination. Once you have actually defined the universe and its decoding, you can define things by some kind of notion of primitive recursion on the universe. It's called universe elimination, and it was actually never there in Martin Löw's own papers, but it's sometimes used by later people, and it makes perfectly good sense. And in our papers on induction recursion, we discuss it quite a lot. Such things tend to be hard to type in intentional type theory, because they're quite complex dependent types, and you easily get into type checking problems. So although it seems like a great idea, it's not as useful as one might have hoped. I mean, I must tell you about, there is something called the dependent types nightmare. And that means when you get too enthusiastic about dependent types, and all of a sudden you realize that, it's so hard to type check things. And there is a little bit of a difference between the Coq culture and Agda culture, is my impression, that in Coq one is careful with not using too many dependent types. So a lot of things are happening by defining type in the ordinary sim type to the simply typed lambda calculus, and then you define relations on top of it, and that's somehow, then you don't get into the dependent types nightmare. But of course, in some sense, it is more beautiful to try to use the dependent types as much as possible, and there are people who are specialists in this craft, and when it works, it's very, very elegant. Right. So now you have seen the first inductive recursive definition. And the only thing I wanted to say about the general shape of inductive recursive definition is that it's actually a very minor generalization of the schema for inductive types and inductive families. You can, of course, also have inductive recursive families, or with a different name, indexed inductive recursive definitions, and I will show you some later. Okay, so now I have shown you some of the Swedish perspective. I don't think I had anything more to say on that slide. So what's next? So I think, Bob, what you absolutely must know about type theory is that you mustn't forget about extensional type theory. I know, Bob, we are in America, we are not in Europe. We are in what has become the home of extensional type theory, Ithaca, Cornell University. So the European type checkers like Agda, Koch, Idris, Matita, previously Lego, they were all in intentional type theory, some impredicative, some predicative. NewPerl is an example of extensional type theory, which you will hear quite a lot more about when Bob Constable and Mark Bickford come later this week. But since I think it's so important, let me just say what the rules are. The rules are the following, that if you have proved that little a and little b are equal in the sense of that this proposition, this set here is inhabited, then they are also equal in the judgmental sense. So this we call propositional equality or identity. And this is we call judgmental identity. And in intentional type theory, this is also often called definitional equality, but it's not appropriate to call it definitional equality in extensional type theory, because if you have a definitional equality, it's some kind of intuitive requirement that it should be decidable. It shouldn't be some kind of complex reason for why something are equal. It should be possible to somehow determine if something is just somehow equal for definitional reasons. It should be possible just to normalize the things, simplify them optimally much, and check whether they are equal. So that's the one rule. This rule is often called identity or equality reflection. And the other rule is that there is only one proof of let me call it UIP, uniqueness of identity proofs. Identity reflection. This makes the theory stronger and more convenient in certain sense, but it breaks the decidability of the theory. And the way this has usually been proved is by saying that you can, if you have this theory, you can actually, you can have a context where, well, what should we call it? Yeah. So you can have, well, you can have a context where you have an element of the universe which is equal to itself. And then if you can go from this identity to this judgmental identity, you can build a model of the untyped lambda calculus, and then you can create non-normalizing terms, and then you can prove undecidability for this reason. So just to advertise just a very new paper of me and some colleagues that we have a new proof of that saying that you can actually also build a model of the untyped combinatory logic, which has an undecidable notion of equality. And then you can somehow reason about untyped combinatory logic, and you can then decide judgmental equalities in the theory relative to that context. So that's a way to prove that you get an undecidable notion of equality, and that as a consequence, perhaps the theory is not what you want. Perhaps it is.
Question?
Yeah?
In the statement of UIP, do the parameters A, B actually need to be AA or some form of
So I think it is like this. In this theory, it is, of course, the case that if you have proved this, then you can prove that, and hence you can replace equal for equal everywhere. Yeah, so yes. Just to make a sort of general reference to developments in homotopy type theory, that Voevodsky has proposed a theory where he both has one universe containing an extensional notion of equality, satisfying rules like that. He calls it exact equality. And another universe where he has a truly intentional notion of equality, which should perhaps more be understood as some kind of notion of equivalence. Right. Let me see what more I can say here. Oh yeah. I was going to show you something which I think is cool. Sorry, probably not for your generation. So, working just in pure Martin-Lev type theory is, of course, rather inconvenient for several different reasons. So it was more it was more the sort of in principle type of thing, not in practice kind of thing, which Agda and Koch are for. It's very Dybjer. But something you can actually do, which is very, very powerful, is that you can make a constructive model of set theory. This is due to Peter Axel, a very early result of consequence of intuitionistic type theory. So, yeah, CZF. Axel. There was a previous version by the American logician Myhill. Constructive Zermelo Frankel set theory. So the cool thing about this thing is that you can actually define a notion of so-called iterative set, or set in the cumulative hierarchy. I don't know, have you read about set theory, some course in set theory where it's a little bit, of course, everyone knows a little bit naive set theory, but it's maybe not so widespread to know about axiomatic set theory and the axioms of Zermelo-Frankel set theory, which really emphasizes that it's very important about sets that they somehow start from, you have only one set from the beginning, the empty set, and then everything is kind of built up by taking power sets, like that. And all sets, are actually sets of sets of sets of sets. One usually draws this picture, you place a set on some kind of level here, which is called its rank, and one draws a line in the middle called for the so-called ordinals. And then you can define sets up to something here, which is called an inaccessible cardinal. So cardinals are special kinds of ordinals. So whatever that is, it is the most commonly accepted foundation of mathematics. And there are a number of axioms all of them due to Zermelo, except one, which is due to Frankel. This is somehow 1908, and I think this is 1930s. And in this theory, you can somehow encode more or less all of standard mathematics. It's somehow the standard for what is correct mathematics. It's of course something very important. And it's of course a challenge for type theory to relate to this. So this cumulative hierarchy is often called V. So now you can define a constructive version of V in Martin-Lev type theory. So we simply take the three last type formers we defined in that order. We say V is equal to W applied to U and T. What does this say? Well, it says that V, you think of them as constructive representatives of iterative sets, sets of sets of sets of sets. So they are, since they are elements of a W type, they are trees. And the index type, you see, it's very, very general. It's an arbitrary small type in the sense of type theory, not in the sense of iterative sets, but in the sense of set as we had it before. And you know, then the branching then is indexed by, so given an index set in U, we get the branching type by applying the decoding function. So you can see that with U, you can get very arbitrary branching. And for example, you know, U itself can be a W type. Yeah.
Does the Vita and set theory, does that include?
Oh, absolutely. So, you know, here we have the ordinals, you know, and at some stage we get to the ordinal omega, and then we continue, you know, omega plus 1, omega plus 2, omega plus omega, omega to the omega, omega to the epsilon 0, and more somehow esoteric ordinals, and then, you know, ordinary set theory goes up to a certain stage, but then there is the world of large cardinals up here, which require additional axioms. But it certainly contains very large sets, you know, like sets of uncountable cardinality, and, you know, there are many uncountable cardinalities, aleph 0, aleph 1, aleph omega, etc., right? There is a sort of whole world of complexity that's classical set theory. But what's somehow very interesting is that we can somehow get some constructive analog of this, where we also have such a distinction, you know, where there are somehow things that we can construct constructively, which are sort of good data structures, you know, and we have good computable functions on them, which are analogs of these large cardinals. You know, when people say, oh, these large cardinals are completely useless, what do these set theorists work on, this esoteric stuff, you know, so non-constructive. But then we can see, actually, those ideas have been useful in the sense of inspiring people like Anton Setzer to do things up here. And I will show you some next time. So yeah, I shouldn't overrun, so I think I have to stop, sadly.
I'm just wondering, so there is a constructive encoding of ZF, and ZF is the basis of all mathematics?
Yes.
So is all mathematics constructive?
No, CZF is weaker than ZF. There are 3 of the axioms that you cannot justify. I don't remember exactly how many, there are something like 8 or 10 or something axioms, and most of them you can satisfy. I mean, I was going to show you a little bit how, you know, the axiom of infinity, the axiom of pairing, axiom of union, and so on, you know, you can implement them here. But the axioms of power set is an impredicative construction. It's not possible. There is a weaker form of that. The replacement axiom, the Frenkel's axiom, which came later, is also a weaker form. And also the axiom, the so-called separation or comprehension axiom, also has to be specialized. But you can do a lot. And one thing, just before you go to lunch, is that I said before, you know, that it's a very good thing about intuitionistic type theory, the predicative version of it, that it can be understood directly in terms of set theory, where everything is understood in the most possible straightforward way, you know. As I said, numbers are numbers, functions are functions in the set theoretic sense, pairs are pairs in the set theoretic sense, etc., etc. Universe has to be a so-called Grothendieck universe, which you have in category theory. Did you tell them about that, Ed? No. So there is also universes in ordinary set theory. So that's, of course, a little bit unusual, but it is somehow the set theoretic analog. But this interpretation of intuitionistic type theory in classical set theory can be done in the constructive set theory. So since this can itself be interpreted in intuitionistic type theory, we get a self-interpretation. This is interesting. And this is often mentioned as an alternative approach for mathematicians for saying what is good constructive mathematics. And there are treatises on this constructive set theory. There are books about it. Yeah?
So is the U type, the universe, the cardinality of that universe?
Is that?
You said there's a simple set theoretic model
Yeah.
for all the types.
Yes.
The U type you define is the inductive recursive.
Yeah.
That type must have a very large set.
Yes, it cannot. I mean, if you in the most straightforward interpretation, where you have full function space interpretation, this will be interpreted by a Grothendieck universe. A Grothendieck universe is something which lives up here, which requires a large cardinal axiom, the first large cardinal axiom, the existence of a so-called inaccessible cardinal. So, yeah, so exactly like that. Yeah, thank you, good question. So impredicative type theory, Koch, doesn't have a straightforward set theoretic model in this way, which was proved by John Reynolds. That's also good for your general knowledge to know. They can have, they have more somehow constructive models, so-called realizability models, which both of the theories have. But it's very good that Martin-Lev type theory can be understood directly as a standard mathematical thing. Okay, I think you're all extremely hungry, so see you tomorrow.